Within just 3 decades, quantum mechanics and Einstein's theory of relativity flipped the entire field of physics upside down. Fast forward to today, and no physicist would dare say our knowledge of the universe is even close to complete. You are watching Documentary. Today I'm taking you on a journey through the 18 biggest unsolved mysteries in physics. Let's start with very basic. Why is there an arrow of time? Time moves forward because a property of the universe called entropy, roughly defined as the level of disorder, only increases. And so there is no way to reverse a rise in entropy after it has occurred. The fact that entropy increases is a matter of logic. There are more disordered arrangements of particles than there are ordered arrangements, and so as things change, they tend to fall into disarray. But the underlying question here is, why was entropy so low in the past? Put differently, why was the universe so ordered at its beginning, when a huge amount of energy was crammed together in a small amount of space? Physicists call it the thermodynamic arrow of time. This concept is tied to the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease over time. At the moment of the Big Bang, the universe was in a state of extremely low entropy, a perfect order that has been unraveling ever since. But why this initial state was so ordered remains one of the biggest puzzles in physics. How about imbalanced distribution of matter and antimatter? Why is there more matter than antimatter? One assumes the universe would treat matter and antimatter symmetrically, and thus that, at the moment of the Big Bang, equal amounts of matter and antimatter should have been produced. But if that had happened, there would have been a total annihilation of both. Protons would have cancelled with antiprotons, electrons with anti-electrons, positrons, neutrons with antineutrons, and so on, leaving behind a dull sea of photons in a matterless expanse. For some reason, there was excess matter that didn't get annihilated, and here we are. For this, there is no accepted explanation. The most detailed test to date of the differences between matter and antimatter, announced in August 2015, confirm they are mirror images of each other, providing exactly 0 new paths toward understanding the mystery of why matter is far more common. So why did matter win this cosmic battle? Some theories suggest that tiny asymmetries in the laws of physics could have tipped the balance ever so slightly in favor of matter. Others propose that unknown particles or forces might have played a role in this imbalance. In the strange realm of electrons, photons, and other fundamental particles, quantum mechanics reigns supreme. Unlike the predictable behavior of tiny balls in classical physics, these particles exhibit a wave-like nature spreading over a large area. Each particle is described by a wave function, a probability distribution that indicates the likelihood of its location, velocity, and other properties, without definitively stating what those properties are. Imagine a particle existing in a state of multiple possibilities, both here and there, fast and slow. This superposition remains until we intervene. The moment we measure a particular property, such as the particle's location, something extraordinary happens. The wave function collapses, and the particle adopts one specific state. But how and why does this act of measurement cause the collapse? This enigma, known as the measurement problem, challenges our very perception of reality. Is reality a construct that only solidifies under observation, or is there a deeper, unseen mechanism at play? Some theories suggest the involvement of consciousness, while others propose hidden variables or parallel universes. When physicists assume all the elementary particles are actually one-dimensional loops, or strings, each of which vibrates at a different frequency, physics gets much easier. String theory allows physicists to reconcile the laws governing particles, called quantum mechanics, with the laws governing spacetime, called general relativity, and to unify the 4 fundamental forces of nature into a single framework. But the problem is, string theory can only work in a universe with 10 or 11 dimensions, 3 large spatial ones, 6 or 7 compacted spatial ones, and a time dimension. The compacted spatial dimensions, as well as the vibrating strings themselves, are about 1 billionth of a trillionth of the size of an atomic nucleus. There's no conceivable way to detect anything that small, and so there's no known way to experimentally validate or invalidate string theory. Is there order in chaos? Physicists can't exactly solve the set of equations that describes the behavior of fluids, from water to air to all other liquids and gases. In fact, it isn't known whether a general solution of the so-called Navier-Stokes equations even exists, or, if there is a solution, whether it describes fluids everywhere, or contains inherently unknowable points called singularities. Is the weather merely difficult to predict, or inherently unpredictable? Does turbulence transcend mathematical description, or does it all make sense when you tackle it with the right math? As we traverse further into the mysteries of physics, we question, do the universe's forces merge into one? The universe experiences four fundamental forces: electromagnetism, the strong nuclear force, the weak interaction, also known as the weak nuclear force, and gravity. To date, physicists know that if you turn up the energy enough, for example inside a particle accelerator, three of those forces unify and become a single force. Physicists have successfully run particle accelerators and unified the electromagnetic force and weak interactions, and at higher energies, the same thing should happen with the strong nuclear force, and eventually, gravity. But even though theories suggest that should happen, nature doesn't always oblige. So far, no particle accelerator has reached energies high enough to unify the strong force with electromagnetism and the weak interaction. Including gravity would require even more energy. To reach grand unification energies, particles would need at least 1 trillion times as much, so physicists are left to hunt for indirect evidence of such theories. Besides the issue of energies, grand unified theories still have some problems because they predict other observations that so far haven't panned out. It's possible we just don't have a powerful enough particle accelerator. Or physicists could be wrong about how the universe works. Next, we talk about what happens inside a black hole. According to current theories, once we cross the event horizon, the boundary beyond which nothing can escape, the gravitational pull of a black hole is so immense that its escape velocity surpasses the speed of light, the fastest thing in the universe. Yet quantum mechanics offers a perplexing twist. It suggests that quantum information can't be destroyed. If you annihilate this information somehow, something goes haywire, explains Robert McNeese, an associate professor of physics at Loyola University, Chicago. Quantum information differs from the binary data on our computers or the memories in our brains. Quantum theories don't provide precise details about an object's location or behavior. Instead, they offer probabilities, the likelihood of various outcomes. These probabilities must add up to 1 or 100%, a concept known as unitarity. If you know the end state of a system, you can theoretically calculate its initial state. To describe a black hole, you only need 3 properties: mass, angular momentum, if it's spinning, and charge. Nothing emerges from a black hole except a faint trickle of thermal radiation, known as Hawking radiation. As far as anyone knows, there's no way to reverse engineer this process to determine what the black hole has consumed. The information seems irretrievably lost, creating an information paradox. However, quantum theory insists that information can't be entirely obliterated. Stephen Hawking and Malcolm Perry, among others, have tackled this paradox. In 2015, they proposed that the information might not be trapped inside the black hole's depths, but rather stored on its boundary, the event horizon. A singularity occurs when some property of a thing is infinite, and so the laws of physics as we know them break down. At the center of black holes lies a point that is infinitely teensy and dense, packed with a finite amount of matter, a point called a singularity. In mathematics, singularities come up all the time. Dividing by 0 is one instance, and a vertical line on a coordinate plane has an infinite slope. In fact, the slope of a vertical line is just undefined. But what would a singularity look like? And how would it interact with the rest of the universe? What does it mean to say that something has no real surface and is infinitely small? A naked singularity is one that can interact with the rest of the universe. At first glance, you might think the problem of naked singularities is partly solved for black holes at least, Since nothing can get out of the event horizon and the singularity can't affect the rest of the universe, it is clothed, so to speak, while a naked singularity is a black hole without an event horizon. But whether singularities can form without an event horizon is still an open question. And if they can exist, then Albert Einstein's theory of general relativity will need a revision, because it breaks down when systems are too close to a singularity. Naked singularities might also function as wormholes, which would also be time machines, though there's no evidence for this in nature. But there's another problem that perplexes physicists: violating charge-parity symmetry. If you swap a particle with its antimatter sibling, the laws of physics should remain the same. So, for example, the positively charged proton should look the same as a negatively charged antiproton. That's the principle of charge symmetry. If you swap left and right, again, the laws of physics should look the same. That's parity symmetry. Together, the two are called CP symmetry. Most of the time, this physics rule is not violated. However, certain exotic particles violate this symmetry. McNeese said, "That's why it's strange." "There shouldn't be any violations of CP in quantum mechanics," he said. "We don't know why that is." While particle physics questions account for many unsolved problems, some mysteries can be observed on a benchtop lab setup. One such enigma is sonoluminescence. Imagine taking some water and hitting it with sound waves. What happens next is nothing short of magical. Bubbles form in the water, creating low-pressure regions surrounded by high pressure. The surrounding pressure forces these bubbles to collapse rapidly. And in that brief moment of collapse, something extraordinary occurs. The bubbles emit light in flashes lasting mere trillionths of a second. But what is the source of this light? This is where the mystery deepens. Theories abound, from tiny nuclear fusion reactions to electrical discharges, or even compression heating of the gases inside the bubbles. Physicists have measured astonishingly high temperatures inside these collapsing bubbles, reaching tens of thousands of degrees Fahrenheit. They've captured numerous images of the light produced, yet no theory has definitively explained how sound waves create these lights in a bubble. The Standard Model is one of the most successful physical theories ever devised. It's been standing up to experiments to test it for 4 decades, and new experiments keep showing that it is correct. The Standard Model describes the behavior of the particles that make up everything around us, as well as explaining why, for example, particles have mass. In fact, the discovery of the Higgs boson, a particle that gives matter its mass, in 2012, was a historic milestone because it confirmed the long-standing prediction of its existence. But the Standard Model doesn't explain everything. The Standard Model has made many successful predictions. For example, the Higgs boson, the W and Z boson, which mediate the weak interactions that govern radioactivity, and quarks among them. So it is difficult to see where physics might go beyond it. That said, most physicists agree that the Standard Model is not complete. There are several contenders for new, more complete models. String theory is one such model, but so far, none of these have been conclusively verified by experiments. Dimensionless constants are numbers that don't have units attached to them. The speed of light, for example, is a fundamental constant measured in units of meters per second, or 186,282 miles per second. Unlike the speed of light, dimensionless constants have no units, and they can be measured, but they can't be derived from theories, whereas constants like the speed of light can be. In his book, Just 6 Numbers, The Deep Forces That Shape the Universe, astronomer Martin Rees focuses on certain dimensionless constants he considers fundamental to physics. These numbers hold the key to understanding the very structure of our universe. In fact, there are many more than 6. About 25 exist in the Standard Model. These constants govern the strengths of the fundamental forces, the masses of elementary particles, and even the rate of expansion of the universe. Why do these constants have the specific values they do? And what would happen if they were different? Unlike other fundamental forces, gravity doesn't fit neatly into the framework of particle physics. Electromagnetism, for example, is mediated by the exchange of photons. The weak nuclear force operates through W and Z bosons, while gluons carry the strong nuclear force that binds atomic nuclei. These forces can be quantized, meaning they are expressed as individual particles with discrete values. Gravity, however, eludes this neat categorization. Theoretically, it should be carried by a hypothetical, massless particle known as the graviton. But despite extensive searches, gravitons have not been detected. They interact with matter so rarely that they would be nearly invisible against the background noise of our particle detectors. The mystery deepens when we consider the nature of gravitons. If they exist, they could be massless, or if they have mass, it would be minuscule, smaller than that of even neutrinos, which are among the lightest known particles. Some physicists, like Theodor Kaluza and Oskar Klein, have proposed that gravity might operate in extra dimensions beyond the familiar 3 of space and 1 of time. Do we live in a false vacuum? The universe seems relatively stable. After all, it's been around for about 13.8 billion years. But what if the whole thing were a massive accident? It all starts with the Higgs boson and the universe's vacuum. Vacuum, or empty space, should be the lowest possible energy state because there's nothing in it. Meanwhile, the Higgs boson, via the so-called Higgs field, gives everything its mass. Writing in the journal Physics, Alexander Kusenko, a professor of physics and astronomy at the University of California, Los Angeles, said the energy state of the vacuum can be calculated from the potential energy of the Higgs field and the masses of the Higgs and top quark, a fundamental particle. So far, those calculations appear to show that the universe's vacuum might not be in the lowest possible energy state. That would mean it's a false vacuum. If that's true, our universe might not be stable, because a false vacuum can be knocked into a lower energy state by a sufficiently violent and high energy event. If that were to happen, there would be a phenomenon called bubble nucleation. A sphere of lower energy vacuum would start growing at the speed of light. Nothing, not even matter itself, would survive. Effectively, we'd be replacing the universe with another one, which might have very different physical laws. That sounds scary, but given that the universe is still here, clearly there hasn't been such an event yet, and astronomers have seen gamma-ray bursts, supernovas, and quasars, all of which are pretty energetic. So it's probably unlikely enough that we wouldn't need to worry. That said, the idea of a false vacuum means that our universe might have popped into existence in just that way when a previous universe's false vacuum was knocked into a lower energy state. Now, what is the fate of the universe? The fate of the universe strongly depends on a factor of unknown value called omega, a measure of the density of matter and energy throughout the cosmos. If omega is greater than 1, then space-time would be closed, like the surface of an enormous sphere. If there is no dark energy, such a universe would eventually stop expanding and would instead start contracting, eventually collapsing in on itself in an event dubbed the Big Crunch. If the universe is closed but there is dark energy, the spherical universe would expand forever. Alternatively, if omega is less than 1, then the geometry of space would be open, like the surface of a saddle. In this case, its ultimate fate is the Big Freeze, followed by the Big Rip. First, the universe's outward acceleration would tear galaxies and stars apart, leaving all matter frigid and alone. Next, the acceleration would grow so strong that it would overwhelm the effects of the forces that hold atoms together, and everything would be wrenched apart. If omega equals, the universe would be flat, extending like an infinite plane in all directions. Astrophysical data suggests that space-time might be flat rather than curved, and thus it could extend infinitely. If this is true, then what we think of as the universe is merely one patch in an infinitely large cosmic quilt, often referred to as the quilted multiverse. At the same time, the laws of quantum mechanics dictate that there are only a finite number of possible particle configurations within each cosmic patch, approximately 10 to the power 10, then again power to 122. Given an infinite number of cosmic patches, the particle arrangements within them must repeat infinitely many times over. This implies that there are infinitely many parallel universes, cosmic patches that are exactly the same as ours, containing someone exactly like you, as well as patches that differ by just one particle's position, patches that differ by two particles' positions, and so on, down to patches that are entirely different from ours. Is there something fundamentally flawed with this logic, or could its bizarre outcome be true? And if it is true, how might we ever detect the presence of these parallel universes? As we continue our journey through the biggest unsolved mysteries in physics, we arrive at the enigma of dark matter. Evidently, about 84% of the matter in the universe does not absorb or emit light. Dark matter, as it is called, cannot be seen directly, and it hasn't yet been detected by indirect means either. Instead, dark matter's existence and properties are inferred from its gravitational effects on visible matter, radiation, and the structure of the universe. This shadowy substance is thought to pervade the outskirts of galaxies and may be composed of weakly interacting massive particles, or WIMPs. Worldwide, there are several detectors on the lookout for WIMPs, but so far, not one has been found. One recent study suggests dark matter might form long, fine-grained streams throughout the universe, and that such streams might radiate out from Earth like hairs. No matter how astrophysicists crunch the numbers, the universe simply doesn't add up. Even though gravity is pulling inward on space-time, the fabric of the cosmos, it keeps expanding outward faster and faster. To account for this, astrophysicists have proposed an invisible agent that counteracts gravity by pushing space-time apart. They call it dark energy. In the most widely accepted model of dark energy, it is a cosmological constant, an inherent property of space itself, which has negative pressure driving space apart. As space expands, more space is created, and with it, more dark energy. Based on the observed rate of expansion, scientists know that the sum of all the dark energy must make up more than 70% of the total contents of the universe. But no one knows how to look for it. The best researchers have been able to do in recent years is narrow in a bit on where dark energy might be hiding, which was the topic of a study released in August 2015. This invisible force, pushing the universe to expand at an accelerating rate, remains one of the most profound puzzles in modern cosmology.